Quantum teleportation is not science fiction. It is a real phenomenon that exists within the framework of quantum physics. When most people hear the word teleportation, they picture something from a movie or a TV show. A person steps into a machine and vanishes from one place only to appear instantly in another. That image is far from what is actually happening in quantum teleportation, but what is happening is just as mind-bending. It is real, it is proven, and it is one of the most fascinating discoveries in the quantum world. To understand how quantum teleportation works, we first need to break free from the rules of classical physics. In the classical world, things have defined positions. They move in predictable ways. You can know where something is and how fast it is going. But in the quantum world, nothing is definite until it is measured. Particles like electrons and photons can exist in a superposition of states. That means they can be in multiple states at once. This is the first key to understanding quantum teleportation. The second key is entanglement. Quantum entanglement is a phenomenon where two particles become linked in such a way that the state of one particle instantly influences the state of the other. It does not matter how far apart they are. Change one and the other changes too. This happens instantly, faster than the speed of light. Einstein called it spooky action at a distance. Scientists call it entanglement. It is not just a theory. It has been tested and confirmed in laboratories around the world. Now imagine you have a particle. You want to transmit the exact quantum state of this particle to another location, but you cannot just copy the particle. The no-cloning theorem in quantum mechanics says you cannot make an exact copy of an unknown quantum state, so you have to use another method. This is where quantum teleportation comes in. You use entanglement to transmit the quantum state of one particle to another without moving the particle itself. Here is how it works. You start with two entangled particles. Let us call them particle A and particle B. Particle A is with you. Particle B is with someone far away. Now you have a third particle. This is the particle whose state you want to teleport. Let us call it particle C. You perform a special measurement on particles A and C together. This measurement is called a Bell state measurement. When you do this, you destroy the original state of particle C, but that state is not lost. It gets transferred to particle B. The amazing part is that particle B now has the exact quantum state that particle C had. The original state is gone from C and it is now recreated in B. This is teleportation. The information did not travel through space in the traditional sense. It jumped. It moved without moving. It leapt across space instantly because of entanglement. That is quantum teleportation, but it is not magic. It does not violate any laws of physics. It does not allow for faster than light communication. You still need to send some classical information after the measurement. This is what allows the receiver to reconstruct the state. So even though the quantum state transfers instantly, the overall process still requires classical transmission. This keeps it within the bounds of relativity. Quantum teleportation has been demonstrated many times. It started in the lab with photons. Then scientists moved on to atoms and larger systems. In recent years, teleportation has even been achieved over long distances. In 2017, researchers in China teleported quantum information from the ground to a satellite in orbit. That is over 500 kilometers, and it worked. That was a milestone. It showed that quantum teleportation could work in space. It opened the door to a new era of quantum communication. This technology is not just a curiosity. It has real-world applications. The most important one is quantum communication. Quantum teleportation is a key part of building a quantum internet, an internet that is secure in a way that classical systems can